Today we will be looking at polymers. After watching this video, students should be able to explain the properties of polymers, distinguish between types of polymers, and order groups of polymers based off of the strengths of their intermolecular interactions. So, what are polymers? Polymers are large chain-like molecules built from small molecules called monomers, and they form the basis for synthetic fibers, rubbers, and plastics. A polymer can either be described as thermoset or thermoplastic. A thermoset polymer is a substance that when molded to a certain shape under high pressure and temperature cannot be softened again or dissolved. On the other hand, a thermoplastic polymer is a substance that can be remelted after it has been molded. Another key property of polymers is cross-linking, or the existence of covalent bonds between adjacent chains. Cross-linking agents change the physical properties of polymers by bonding carbon atoms on different chains. An example of this phenomenon would be Charles Goodyear's vulcanization process, in which sulfur is added to rubber and heated. The resulting mixture maintains the elasticity of raw rubber, but is much stronger because the sulfur atoms form bridges between polymer chains. And such bridges can be seen right here. Types of polymers. The simplest and best known polymer is polyethylene, which is constructed from ethylene monomers. Properties of polyethylene can be manipulated by substituting ethylene monomers. For example, Teflon, in which these hydrogens would be replaced with fluorine. If you were to compare the intermolecular forces of polyethylene and a substance like polyvinyl chloride, you would expect polyvinyl chloride to have the stronger intermolecular forces because its chlorine atom allows for dipole-dipole interactions. In contrast, the nonpolar polyethylene molecule would be limited to London dispersion forces. Polymers can be copolymer, in which two different types of monomers combine to form a chain, as seen in rows 2 through 5. On the other hand, others can be described as homopolymer, in which monomers of the same type combine to form a chain, like in row 1. A dimer simply refers to two attached monomers, while a polyester is a category of polymers that contains the ester functional group in their main chain. A polyamide is a polymer made by the linkage of an amino group of one molecule to a carboxylic acid group of another. There are two main types of polymerization reactions. In an addition polymerization, monomers simply add together to produce the polymer. The process is initiated by a free radical, which induces another free radical, and the process repeats thousands of times. The chain eventually stops growing when two radicals react to form a bond. So, for example, as you can see, this hydroxyl radical attacks the pi bond of this ethylene molecule. And then on the product side, this free radical is available to attack another ethylene molecule. Meanwhile, in a condensation polymerization, a small molecule, like water, is formed for each addition to the chain. So this first reaction would be considered a condensation polymerization because of the formation of water, while the second one would be considered an addition polymerization, because no such molecule is formed. There are two main polyethylene variants. The first is low-density polyethylene, which contains many branches and is used to manufacture transparent film. The second variant is high-density polyethylene, and it consists of straight-chain molecules that pack tightly. The useful properties of both variants are due to high molecular weight. As a multitude of small attractions between nonpolar points accumulates to a significant value, the physical tangling of the chains also gives the polymer strength. Physical properties like polymer strength and viscosity increase with chain length. However, other physical properties such as color, refractive index, hardness, density, and electrical conductivity are not greatly influenced by the length of the chain. The extent of chain branching also contributes to the physical properties of polymers, in that more branching results in a weaker polymer. This is due to a lack of adjacent chains and a subsequent lack of hydrogen bonding. Varying the substituents also modifies polymer behavior, with an example being varying the arrangement of methyl groups on polypropylene. Arrangements can either be described as isotactic, syndiotactic, or atactic. In an isotactic chain, groups are located on the same side, while in a syndiotactic chain, groups alternate sides. Meanwhile, in an atactic chain, the groups are distributed randomly. And the reality of the situation is that isotactic polypropylene makes stronger fibers than atactic polypropylene, because isotactic chains pack together more closely and therefore are more crystalline. We know that crystallinity, which leads to increased hydrogen bonding, results in a stronger and harder polymer.